Hi, welcome to this new episode in which we will continue cleaning our EEG data. And we saw in the last episode how we can use LV clean segmented to, in an automated way, clean our data. Right now we are going to use another lovely vector function which is called LV manual cleaning, or actually it's a script, but we're going to use it to see how we can manually clean our data. And I have basically included many blocks inside of this script. It's not really a function. I have put it in a script such that you can comment out anything that you don't want to use, because it has different cleaning steps, so you might not need all of them, so you have the freedom to comment some of them. So anyway, we can look at this script and see what this script is doing. So in every block we have different cleaning process that we can apply on our data, so it would entirely depend on the kind of effect that you want to see in your data. So here I'm just defining CFG and then specifying that the method will be pre-classification, and then calling a function that is called reduce trials in LV. So we can control D and look inside this function, and we can see this case pre-classification. So let's continue our debugging and look at this. And this part I was just trying to put some um, options in a list in case you didn't specify cfg.method. But anyway, I do encourage you to specify the exact method that you want to try. And then we enter this switch. We have our method to be pre-classification, and in this function we are acting on the second dimension. So basically, when we extract like the variance in time, then we will have a matrix with trials and then channels in the second dimension. So what this will do, it will basically loop on the second dimension, and then it will get every column. So it will get all rows from the first column, and then it will get the distribution from that, and then it will get like the first and third quartile like we did last time. So basically we got all measures. That's a trial by channel dimension, and then we will have every column, and then we will get the first and third quartile from this data, and then we will locate the outliers. So here we calculate the interquartile range Q1 and Q3, the percentiles, and then we will end up with the two like the lower threshold and the upper threshold for our data, and anything outside of this range is bad. So here we are defining a boolean which will be a 2D array. It will be a matrix containing any element that falls within the range, within the expected range, so basically the non-outlier elements. And then we repeat this for all of our columns. So basically that's the first column. If we repeat this, this will fill in the second column, and so on until we finish the 12 the 12 columns that we have, the 12 channels. So right now I'm just putting this inside of good trials because I'm returning good trials from this one, and that's how we step out of this function, by returning good trials matrix. So right now this should be, yes, trial by channel data containing the good elements, and anything else will be 0. Okay, so we can do this for any measures, and you can do this for any kind of data that you might have. So it doesn't have to be trial by channel. It can be any sort of data, but the thing is, it's acting on the second dimension. It's looping on the second dimension, and you are creating the distribution based on the values of the first dimension. And so we can do this for the variance, and we can do this for the other measures as well. So we can do this and extract this for the variance in a different matrix, can do this for maximum and do this for minimum. Right now I have 4 of these, and I can AND all of them such that I only trust an element if it's good in every of these matrices. If it's bad on just one of them, it will be a bad trial channel element. So now we would have this aggregated matrix, and we can look at this matrix and see what is going on in this one. So we can threshold this one and say that, okay, we know that this is trial and this is channel. If we get anything that is bad on more than, so it's 0 on more than 25% of the channels, then this is a potential bad trial, and that's exactly what this line is doing. So I'm basically negating what we have because this is good flag, so I'm just flipping all zeros and ones, and then any 0 would be 1 and any 1 would be 0, and then I'm just summing this of the on the second dimension, so the columns, and so we will have trial by 1, so it will be just one column coming from this one, and we can actually verify this if you would like. So I just copied this one and I can execute it alone. And I do encourage you to do this because sometimes you are putting a lot of steps in the same line. So the SS should be yes, trials by 1, and it's containing the result of this summation. So basically now we need to know if this number, which is the number of bad channels, is higher than 25% of the size. I can press F2 as we said before to execute this, and this will be 3. So anything that is higher than 3 will be bad, and these are the possible bad trials. So for instance, this one was bad, and you can see that this number appeared here. Okay, and then we can enter the second section. So in the second section we are trying to use reduced trials, the same function but in a different way. So in this one we are trying to loop on our second dimension, which is channels. So back to our let's go back to our golden tensor such that we do not forget which one we're talking about. So data to trial, and we are acting on this slice. What this is doing is that we are getting the first channel in the first iteration, of course. So let's go to our golden tensor for a moment. Okay, so going to our golden tensor, we will see that we have trial, channel, and then time dimensions. And what the code is really doing, it was, as I said, taking one slice of channels. What this means is that we're taking one channel, so one data, and then we're taking one slice. This slice is trial time slice because we are getting just one channel. We are not getting a lot of channels, just one channel, so we are just getting this slice. So it will be a matrix of trial and time. Okay, now that we have seen that we have this trial time slice, what I want to do in this one, I'm just squeezing out the singular dimension, so it's the channels, so it will be really a trial time dimension. And right now I want to act on a different dimension. So basically what I'm doing here, and instead of putting channels on the second dimension, I am putting time. So basically we are looping on every time point, and for every time point we are trying to see which trial is representing an outlier. So after doing this, we can see that we will have a trial by time dimension, and of course we are inside of just one channel, the first channel, and we can negate this. So I want to look at the bad time points. So what I'm doing here, I'm just negating all the zeros and ones, and then I'm taking the summation in time. So it will be just one long vector representing trials, and here is the summation, or the count of how many time points are being considered as outliers. And after doing that, we can now do a distribution on this one, like on this value. And because we are counting how many of them are bad. We're only interested on the upper bound uh, of this sort of analysis, because we are interested on how many of them are bad, and we are counting this, so it's always greater than zero. So I just wanted to do this with the large thresholding. So I will be considering Q3, the third quartile, and will be calculating the interquartile range, and anything going above the third quartile will be considered as an outlier. So this will give the potential outliers for this particular channel, and then if we continue our loop, it will do the exact same thing for all of them. So we'll end up with this matrix, and then we will be able to threshold this matrix. So then we will be able to count how many of these are bad by doing the same, by applying the same technique basically, but right now we're looking at the bad ones. So these are the possible bad trials based on this rejection of individual time points. Some of these analyses will be stringent, and some of them are not very stringent, so it's totally up to you which ones you would like to try. Okay, the next section. Okay, so in this next section, I wanted to identify the bad channels in the majority of trials. So basically what I'm trying to do here, I'm just trying to extract the same thing that we did before, but instead of looking at this as trial by channel, I want to look at the result as channel by trial. So if we have a lot of channels and we are able to do this kind of distribution on the channels, it will be perhaps useful to do it in this way. So here I am just transposing my matrix such that it will become a channel by trials, and we can look at this. It will be channels by trials, channels by trials, and we can close all except this one. Yep. Okay, so right now we can loop on our second dimension, and we can do the distribution and interquartile range and so on, and define our outliers. I think that it makes it easier to just manipulate dimensions and then reuse the same function. So I really do encourage you to think about like a new cleaning technique that you would like to apply, and put whatever you want to iterate on in the second dimension, and whatever you would like to have as something to distribute, and just look at the distribution in the first dimension, and you can apply whatever you would like to apply. So for instance, we can apply our same measures like the mean, variance, maximum, and minimum, but after transposing these dimensions, we will be acting on our we will be looping on our second dimension, but we will be acting and looking at the distribution of the first dimension. So we will basically looking at the distribution of channels. This might be useful because you might be thinking that all of your channels should be having roughly the same scale, such that if you find one channel that is really going very high compared to the other channels, then this is a potential bad channel. But before doing this, in the previous sections, we were looking at if a time point is bad on a specific channel. So we were always looping on the channels. But the thing is, if one channel is going bad all the time, and you are always looking inside of this channel, you will not be able to figure out if this channel is an outlier in general. What I mean by that, if this channel compared to a neighboring channel is really an outlier, because it could be having a very high scale compared to other channels all the time, and you couldn't figure out just because of this bias, because if it's really an outlier all the time, then the mean or the median of this channel will also be very high, and then you wouldn't be able to catch such an outlier. But with this analysis, when we look at every channel like so and compare them to other channels, we will be able to detect such abnormality in our data. So we can, after transposing them, we can reuse the same function again. And right now I'm comparing this to like the majority of trials that we have. So basically I don't want to have the same threshold of 25%. You can do whatever you want on this one. Here I wanted to have it like the channel should be an outlier lower than the majority, and then I will only trust it. Otherwise it's a potential bad channel. So basically we are looking at this part, and we can see that if we look at this, if the summation of the good points is lower than the the half of basically half the number of trials that we have, then we have the minority of trials being good in this channel. Then this is a potential bad channel. So basically we can continue on this, and I'm here just displaying which channel is bad. So for the mean, for the average measure, none of them were bad, and I'm just repeating this for the variance. For the variance, none, and for the maximum, none, and for the minimum, none. So with this we can be now sure that none of the channels is bad. And I have added another way to look at this by scattering our channels. So in this one we try, okay, let's step inside this one and see. So we have data.trial, we have our golden tensor, and we have trial channel dimension, trial channel time, and then we take the mean. We take the mean in the third dimension, so we'll end up with trial channel. And then we take the median in the first dimension. When we take the median in the first dimension, then we will have 1 by the number of channels, basically. So this would be 1 by 12. So it's indeed 1 by the number of channels. And we can place a breakpoint here. I'm just now creating a figure, and I am scattering my data points on this figure. So I'm just scattering all of them, and I'm just putting this in a subplot, and I will be putting data from other measures as well. So I will just continue this part, and now we will have our figure looking like that. And as you see, we cannot really like visually see if any of these channels is bad, because all of them are like aggregated and scattered next to each other. But anyway, let's say if you are really being very stringent with your data and you feel like this is an outlier, I'm defining some variables, so v1, v2, v3, v4. So basically each one of them is representing a measure, and you can check that. So that's v1, v2, v3, v4. So v4 is corresponding to the minimum, v3 to the maximum, v2 to variance, v1 to mean. So basically if we are looking at v4, then we are looking at the final one, which is the minimum. So perhaps the minimum of this channel is an outlier. So I can basically export this and name it v4. Okay, and I can just close this. Okay, so right now if we look at our workspace, we will see v4, and it will be defining both x and y axes. So here I'm just checking v4 with the corresponding points and which channel was corresponding to this. So here I'm just checking if this variable exists, and none of them exist but v4, and that's why we're gonna access this channel and see which channel is bad. So we're basically putting this inside of this matrix here. As we can see, scattered minimum is now CB6. So CB6 is a potential bad channel that we have. And then of course you can later on choose your channels with a FieldTrip select data function, or you can keep it. It's always up to you. But the thing is, now you have that this is a possible bad channel, you can reject it.